All right, everyone. Thank you for your invitation, and I do apologize. I have a hard stop at about 45 minutes after the hour, so thank you for joining early. This is a presentation that you had requested from a selection that I provided. The material is actually created and delivered in about 2010. It is a summary of work from quite a few of my students at that time. We were working on the problem of tight gas and the early work on gas shales. This work does not represent a significant loss in technology relative to the current practice. In fact, it's about the same. There are a few more models, there are a few more methodologies, but the fundamental approaches for the analysis of well performance for tight gas and shale gas is essentially the same as what I'll cover now. The biggest difference, of course, is that now instead of a single vertical well with a hydraulic fracture, a single hydraulic fracture, we have horizontal wells with multiple hydraulic fractures, sometimes as many as 100 stages of hydraulic fracturing, which greatly complicates the analysis interpretation. So as we begin, you've already given me a nice bio, so thank you. I'll jump over mine. That's what I look like now. I got old. And the first paper that we will talk about is SPE 110187. This particular paper was one where we began looking at these tight gas wells. This is a little bit pre-shale, if you want to think about it like that. The permeability of these reservoirs was very low, sometimes as low as 1/1000th of a millidarcy, so 1 microdarcy. But the approach was that we had developed an elliptical model for the analysis of a single well, and we performed analysis using this elliptical model on several field cases. We're very fortunate at the time that there was a major play in East Texas called the Bossier Shale, which is actually part of the Haynesville Shale. And inside of the Bossier Shale, there's a lot of lenticular sand type reservoirs. They are not pervasive. They kind of come and they go. But this particular company had developed a lot of these very tight, almost shale gas wells with hydraulic fracturing, and they had noticed that the completion size or the size of the stimulation, more to point, greatly affected the overall performance and recovery. Now, all this is obvious looking back, but at the time they wanted to know, could we estimate reservoir properties? Could we see if there was an issue with reservoir properties relative to that? So the goal of this particular work was to perform the production and data analysis using elliptical flow model, and then come back and compare the results being the permeability, the fracture half length, and then the eccentricity, or how fat the ellipse is. So the ellipse could be almost like a line or a cigar, or it could be really fat like a circle, and we'll take a look. So the very first case was a small stimulation case, and you'll notice that the gas flow rates are extremely well behaved, generally speaking. It's because they didn't have a lot of shut-ins in this field. You can see the calculated bottom hole pressures are down here. There's some disagreement between the calculated model-based pressure and the actual or the calculated bottom hole pressure from a methodology, but we sort of attributed that to some of these wells produced water, and sometimes there was liquid loading. You can see that as the well got older, there was more and more jumping around, which is indicative of liquid loading. But as far as the signature of this data set looks excellent, and both for the pressure and for the rate. So it was history matched using this elliptical model. The analysis was performed using the elliptical model over on the left-hand side, and there was history matched using essentially the same kind of a model. It was more of a shoebox model, a rectangle for the limits of the reservoir, but for all intents and purposes, it was quite similar. So as you look, you can see the clarity. The black data are the rates or the productivity index, the rate divided by the pressure drop, and then the blue is its integral, and then the red is the derivative of the blue. So it's sort of a well testing analog, and you can see generally pretty good match. The permeability is quite low. It was 0.0097 millidarcies. Fracture half length is about 129 feet. The eccentricity is 2, so it was sort of near circular. And then the gas in place that we calculated for this well was approximately 1.3 BCF. So this would have been a modest well, sort of a low recovery well. The initial gas rate was on the order of 2 million cubic feet a day, and then came down very nicely over the course of almost 5 years, still maintaining a good production history all the way through. The next was a large stimulation treatment, and this time what you'll notice is that the rates are significantly higher over in this region, and then there's some sort of a situation here. We assumed this had to do with liquid loading. Probably the tubing was not being unloaded properly, and this affected both the rates and the pressures, and then somehow they resolved that and it came sort of back on trend. So looking at the raw data, most people see this and go, oh, something must be wrong with the data. No, it was something to do with the operational approach used in the field. And then we see again the calculated bottom hole pressure, and we can see the differences whenever we have these drops in the rates, which causes an increase in the pressure. And then of course the match coming back over, we see a very nice, very strong match with the rate, reasonably good match with the derivative, and very strong match with the integral derivative. In this case, the permeability is a bit lower actually. The fracture half length is a little bit higher. It is a much higher equivalent conductivity of the hydraulic fracture. The FE is 1000. And then the ellipse this time, because of the lower permeability, is flat. Is sort of it's almost like a circle, or it's approaching a circle. And then the gas in place for this well is much higher. So even though the permeability is smaller, the treatment was much larger. And then we can see that the gas in place that was contacted. You can also see that what I mentioned here is also mentioned in the comments. This had to do with, we believe, a tubing or a packer leak. The next slide shows a hybrid water frac, which was where people were using a little bit of gel to carry proppant. And I'll go through this one really quickly. An excellent match with the rate function, excellent match with the derivative, excellent match with the integral. Pretty good match with the history match model, fair match on the pressure. This was a low-ish permeability situation, higher fracture half length, fairly high effective conductivity, and then the ellipse is getting smaller and smaller, and a smaller contacted gas in place. So a lot of this has to do with how effective the stimulation is. So then what we did is we correlated the results of this. This is just like anything you might do yourself. And what we did is we classified them as small, large, or hybrid. And we're looking at the contacted gas in place. So that's how much gas in place we calculate from the analysis versus the permeability we calculate from the analysis. And we see we have a very nice trend, or an apparent trend, I should say, for the water frac and the hybrid cases. There are multiple small water frac cases that lie off trend. And one could debate that maybe they just were not as pervasive as they could have been. They didn't contact more gas in place. The calculated permeability is still pretty high. If the correlation were unique, these data would be shoved over here, but they're not. So then let's look at the contacted gas in place and the calculated fracture half length. And here we have a much tighter spacing. It could be bias on the part of the analyst. I want to be honest about that, because most people are going to think that the fracture half length should be in the 100 to 300 foot range, maybe an outlier of a little bit higher than that, but you can see almost all these fracture half lengths are within the 100 to 200 foot range. So there could be some bias factored into that on the analyst's part. The next slide shows something kind of interesting, the permeability on the y-axis and then the drainage aspect ratio on the x. And this is a calculated parameter based on how the analyst saw the particular nature of the match with the elliptical flow type curve. So a 3 is exactly a circle, a 2.5 is approximately a circle. Down in the 1.5 to 2 is a fat ellipse, and then down in the 1 is a very thin ellipse. So you can imagine, even looking at these ellipses here, this might be, say, maybe a 1.25, but then if we expanded it, till it was almost circular, it would be a 3. So what this is really saying is that for the lower permeability cases, the drainage aspect ratio is very small, which is what we would expect. We'd expect most of the pressure drop to be coming from near the fracture and not much out in the reservoir. Next is fracture half length, and in this case we're again looking at probably a little bit of bias because all the calculations are between 100 and 200 feet. And then we can see, though, there is some sort of a grouping of trends, and these smaller jobs did have a larger aspect ratio, which could be something to consider in your completion design. It could also be because they were in the higher permeability region. So that closes out the discussion of that paper, and let's go next to the work that we had been trying to solve the case of analyzing. Yes? Is there a question? No? Okay, I'll continue. So next we'll look at SPE 116731. And in this case, what we're looking at is the comparison of exponential and hyperbolic decline relationships, time rate relations for tight gas sands. Now, for those of you that are still students, you've been taught that the hyperbolic decline is almost universal. It's been in use for almost 100 years. It is the most used equation for reserves and so forth. And what we were really trying to do here is understand how to use those relationships for the analysis of reserves, or for the forward prediction, the production predictions, and reserves estimates. So this was a series of papers that we wrote on this topic, of which this particular one was focusing on how to utilize these relationships. So about 2008, a student of mine and I had been working on how to characterize some data for tight gas and shale wells, as I mentioned before. And actually at this point we were also looking at shale gas wells, the Haynesville Shale, the Woodford Shale, the Fayetteville Shale, and the Barnett Shale were fairly large. They were coming to be fairly large contributors to the North American gas state. And we had been looking at these relationships, or trying to decide whether the hyperbolic was the appropriate relationship. So what you're looking at is an equation that was by observation. So we looked at, we actually calculated the derivative, divided by the rate, took the absolute value of it, plotted it, and looked to see if it had a power law trend. That was it a power law function of time? And was there a long-term constant as well? The long-term constant is kind of problematic. The goal in putting a long-term constant was to ensure that this equation did not overpredict. When this particular form is integrated, we obtain the flow rate relationship, which is that rate is equal to some constant multiplied by an exponential of this expression minus this constant times time minus this constant multiplied by time raised to a power. And this is very important because this is sort of a non-intuitive relationship. We estimated this from observed field data. at about the same time, a colleague of ours at Texas A&M had been pursuing a slightly different form, but exactly the same mathematical result of this, called the stretched exponential. And the stretched exponential has been used in a variety of engineering applications, physical applications, since the mid 1800s. It is not a unique solution to the differential equations governing this, but somehow it seems to model this quite well. So again, that was work where someone was looking at it from a statistical standpoint. Here we're looking at it from a diagnostic standpoint. So we were actually trying to determine whether or not the D parameter plotted as a function of time and the B parameter plotted as a function of time, if they had any meaningful characteristics. And we'll show you that in just a moment. So really what we're proposing is that this is an alternative to the modified hyperbolic relationship. So this is one of our cases again from our selection of small water frac, large water frac, and hybrid frac cases. And this is a very busy graph. I apologize for it. We don't put this much data on a graph anymore, but just bear with me. The left-hand axis is the logarithm of the gas flow rate. And you can see that the gas flow rate has significant erratic points. We would call these data noise. I'm certain that everybody on this call has their own idea of how to remove data noise. At that time, we were only removing data noise by hand. That is, we would take this data into a software and we would either point by point or some sort of region select, we would remove the data points that we believe should not be part of the analysis. So for example, if you're watching my mouse, the major part of this data set is here, and that would be the data that we would want to focus on for analysis. Okay, so assuming that we can remove the data points that are not part of the major trend or not, that don't have noise, or we can only focus on the points that we believe represent this major trend. When we take the derivative, as we saw from this expression, and then divide it by rate, we obtain this trend. Now there's two different data sets here. There is one data set which is calculated, as you can see, it says it's from rate or from from rate or from time. And this really confused a lot of people, and I apologize for that, but it's just calculus. The calculation from time is taking the derivative, as you saw, exactly like this. The other calculation uses the rate and the cumulative production. Now in theory, and theory is important here, the mathematics are the same. But in reality, the rate time, or the calculating things with respect to time, is probably going to be better in the long run. Sometimes it's very difficult, especially if there are errors in the earliest data. It'll corrupt the cumulative, and that will make the calculation of those derivatives difficult. But essentially, this is the derivative divided by rate. We're looking to see if it actually breaks away, but for the moment, it just looks like it's a beautiful power law straight line. Well, as you know, the B factor is the derivative of the reciprocal of this function, so it is also going to be a power law straight line, and it is also going to look something like this. So the point of this is that there are a couple of ways to calculate the D and the B, and we've been doing this for about 15 years, where we calculate the D and the B and we compare it with the rate, and we try to establish whether or not we think that's relevant. But this is not something that is easy. It requires some human intervention. I'm certain that there are many of you on this call that are thinking, well, I will send this data set to Python or to R, and they have error rejection algorithms in that software. And you're certainly welcome to do that. I've seen some very nice data sets coming out of Python or R where there are data rejection algorithms that will take out data which are not on trend. But in general, I would want you to learn and practice doing this on your own. So a lot of words there. Apologies if that was too much, but I want to orient you because we're about to look at several of these. So the hyperbolic case is over here. That's what the hyperbolic model does. It just has a characteristic behavior that are very early times is represented by a constant. And then it follows our trend, but we notice out here that it has a slightly different slope. And we also notice that our power law trend has, is a linear behavior the entire path of the data. But if we add this d infinity constant, it can roll out like this. Well, what that d infinity constant does is it causes the rate profile to drop like an exponential. It causes the b, which is calculated as a model parameter, to drop very significantly as well. So this would be essentially putting on the brakes using a dampening coefficient to slow down the extrapolation of this equation. So in a simplistic sense, we have the hyperbolic extrapolation here. We have the power law extrapolation here. Very similar, actually, even out to a very large number of days. But the cumulative difference between these and this lower curve is tremendous. So what we would be looking for is whether or not this black curve has any physical reason to be there. If there's no evidence of a boundary, you can't really impose one. But in our business, we have been imposing boundaries on, or we have been imposing terminal conditions on these equations for a long, long time. Now, in this work, I did not show imposing a terminal condition on the hyperbolic, but we do that as well now. That's very common. So this is a completely different well. I'll go through it very quickly. We can see the rate data. We can see the D as in dog calculated from the rate data. And then we can see the B as in boy calculated from the D as in dog data. And we can see very consistent trends. The extrapolations are all reasonable. There is no deviation from this particular trend, which is the master trend. They all appear to have nice straight lines and no serious issues. There's no evidence of this curving out. There's no evidence of a D infinity being required. So this is very long-term transient flow. And I'm probably not making this very clear, but what this tells you is that for a long time, for almost 5 years, you're still at a very high B factor, well over 1. And being over 1 with your B factor tells you that you're definitely in transient flow. So this particular well, we believe, is still very much so in transient flow, as we did for the other one as well. There does appear to be some stabilization around a B factor of 1 for this case, so that could be evidence that it is trying to have a terminal decline. But over here, we don't see that. We see just a continuous nice trend. So we would suggest this case is still in transient flow. The next case is the so-called hybrid water frac, and again, I'll go through it very quickly. The data here are much more noisy. As you can see, the noise, it isn't as broad a spectrum as we saw before, but it's very, very dense here. There's obviously some concern about that data because there's a lot of data points in this region. So we would take this data, we would clean it up, we would take its derivative, and then what we would look for is, does the derivative actually roll over? If it does, then that tells us we have some sort of a bounding effect or some sort of a termination effect on it. But for this particular case, we do not see that sort of effect. So again, the rate profile, the D as in dog profile, and then the B as in boy profile. And all of these, again, still strongly suggest long-term transient flow, which of course you cannot make a reserved prediction unless you apply a termination criteria. And again, the termination criteria we would use would be that D infinity term for this particular relationship. There's also another formulation of the hyperbolic, which is the green curve shown here, which does have a termination criteria as well. And that again is the most popular equation used, but we didn't present it that way. The next is a student project that actually, I have to say the student owned this quite well. She was a great academic student, and I worried a little bit about whether or not she could do research, but she began working on her research problem with my other student at the time, and I was supervising this, of course, so I knew what they were doing and sharing ideas. But she began working, let's say, on September 1st, and on or about March the 1st, she handed me her thesis and her work product, which was a spreadsheet, and it was both were a work of art. So, I don't want to challenge anyone here to say that you don't need an advisor, but I will tell you that you probably don't need an advisor as much as you think you do if you're very highly motivated to work on a problem. And again, I was there giving ideas, giving guidance. The original concept was mine, of course, but the student ilk was also there, and he was also providing guidance. And we, of course, had discussed this problem in depth before we gave it to her because we weren't sure how to do this. And you're probably wondering, what does continuous estimation of ultimate recovery mean? What that means is we are going to use the data and we're going to calculate and extrapolate at every point what the EUR is. Now, for those of you who haven't done that, calculating and extrapolating at every point seems crazy. It's just going to paint the screen black with all the possible options. And that is true. But it will converge. It will become better and better as time goes on, particularly if you're careful about how you sample this and also how you look at it as constraining the estimates. So we'll talk a little bit about that as well. So we start by looking at the power law exponential relationship, and we jump over to this discussion where the first thing we're going to do is take the rate profile, and we're going to take the error, any of the data that we don't believe should be on there, and we're going to remove it. So this has physically been removed point by point, taking these points out, and now we have this. And you can see it doesn't really affect the cumulative production. The shape and nature of the cumulative production is essentially the same. There isn't any loss of fidelity there. The real question is, what is this feature? Because we're not looking at pressure. So what is continuous EUR? Well, we specify a time segment, and we will fit an equation to that. We specify another time segment, we fit an equation to that. We specify another time segment, and we fit an equation to that. So we would have an equation fitted at 50 days, an equation fitted at 250 days, and an equation fitted at 2,000 days. And we would watch to see how these equations, we'll use different ones. We'll use the hyperbolic and the power law exponential. And we want to see how those extrapolate to ultimate recovery. So this is a very busy graph. Again, I'll walk you through it very carefully, just like we said. There are samples at 50 days, 250 days, and 2,000 days. So looking at the data over the entire interval at 50 days, you would have a fit here. That is a regression analysis here. And then you would have some sort of a matching criteria for your QDB. And then you have another match using at 250 days, still using the hyperbolic relationship. And then at 2,000 days, still using the hyperbolic relationship. So we're really focusing on this little region, seeing how well we match the red. So as time goes on, we match the red better and better, which is telling us that our estimate of EUR will get better and better as well. Now, if we go to the power law exponential, we're looking at exactly the same range of data, only now fitted with a different curve. And you can see, wow, what an excellent match that gives here. Now, whether the extrapolations are correct, we don't know. That remains to be seen. But the match, the consistency of the match using the power law exponential, very, very strong. Okay. So the first time we presented this, we had a person in the audience. It was an exam, if you want to call it that. It was an exam presentation. And that person said, well, this is great, but this method always over predicts EUR because you can see the values are getting smaller. The first one was 6, then 5, then 3. It was 3, 3, and 3, so that was pretty good. But then he said, you should come up with a method that under predicts EUR and converges on the right answer. Well, he was right, of course. That's why it's nice to have discussions with your colleagues. But the first extrapolation is extremely low. The next extrapolation is still low. But then once you're out here with a large volume of data, you can see that your extrapolation is very small, and the physical extrapolation length and your value should be reasonable. So again, progressing in time, 50 days, 6 BCF, 3 BCF, 0.3 BCF, 250 days, 5 BCF, 3 BCF, 1.3 BCF, 2,000 days, 3 BCF, 3 BCF, 2.6 BCF. So pretty good converging approach. One of the comments I would make on this is you really need to keep your mind focused on not trying to overthink this. You're not trying to get a perfect answer. You're trying to get a representative answer with this methodology. Now, can this be done by hand? Yes. Has it been automated in a software? The answer is yes. That software is not available to the public. Unfortunately, we developed it for the operator and they haven't shared it. But that software requires a lot of command and control. You have to be very careful and not allow it too much flexibility whenever it's making its calculations. So in summary, we have all of these different curves fitted over different times for the hyperbolic equation, all these different curves fitted over different times for the parallel exponential, and you can see they're almost identical in every case. And then lastly, we show all the extrapolations of the rate versus cumulative plots, so even the very early ones, and they progress out. So what we would be looking at is, surprisingly, the parallel exponential didn't really change over time. So this is the expression for the parallel exponential. In other words, it was pretty much on average immediately. Now this is an unusual case. We selected it because we worked in details and so on, but it worked out pretty well. And you can see the characteristic behavior for the hyperbolic. It comes in high and then rapidly drops. And then we can see the other methodology comes in low and slowly increases until it also converges. Now, some of you are probably saying, why would you do this? This is a lot of work for relatively no gain. And the reason we did this was because we were trying to figure out what the band of the EUR extrapolation would be. In other words, what are the actual reserves? And what had happened is we had been in a meeting where someone showed reserves taken at the first, I don't recall, maybe it was 2 or 3 months, and the number was astronomical. It was way up here. It was in the 20s. And then at 6 months, it had dropped into the teens, and at 9 months, it had dropped to about 10, and then at a year, it dropped about here. And so the estimated gas in place for that particular problem started out at 20 BCF and ended up somewhere around 5. So that's a 4-to-1 drop in estimated reserves. So imagine if you went to your boss and said, you know, I've calculated 20 units of gas for this. And then you come back to your boss a year later and say, I made a mistake. There's not 20 units. There's only 5. He's not going to be very happy with you. And again, that was why we created this methodology, was to watch this calculated EUR evolve in time. So next is a really quick study of something called the hybrid decline models. I just wanted to put this in here so that you would see, again, we go back to the ILK model, which is the parallel exponential. But now we're going to try some other cases. ILK, this was the subject of his dissertation, and at one point he had 8 of his own equations that he had built. That's 8. That's 2 less fingers on your hands that you have, or I guess that's the exact number of fingers you have plus 2 thumbs. And the reason he was doing this is because he was working with data and he was trying to establish what he thought was the best overall rate equation. And his conclusion, of course, was that there is no perfect rate equation. So he has this particular model, which has an exponential, a parallel exponential, and then a terminal hyperbolic. And then later on, he has combinations of others. So model number 1, if I wasn't clear, is the parallel exponential. So that's model number 1. Model number 2 is this parallel exponential combined with a hyperbolic. So it's normalized by a hyperbolic, if you want to think about it. And then model number 3 is the parallel exponential coupled with, it's an analytical model for gas behavior. And this model is really ugly, but it's actually fairly easy to use. So it's essentially saying during transient flow, we'll use the parallel exponential, and during boundary dominated flow, we'll use this analytical model. So again, model 1, Model 2, and Model 3. And let's see how they compare. So, of course, wouldn't show it to you unless it worked. But in this particular case, we can show that we have the gas rate data and the cumulative production data. Gas rates on the left axis, cumulative production's on the right. And we fitted Model 1, 2, and 3 through the data. Generally looks very good through transient flow. Almost everything is perfectly matched. And then we come out of transient flow and we have significant differences in overall extrapolations. But who's to say which one of these is correct? And of course, this is on a logarithmic scale, so you can see that whenever we extrapolate, there isn't that much difference. It's something on the order of 2 BCF, maybe a little bit higher or a little bit lower. But the actual rate extrapolations is hard to differentiate out here when you don't actually have any data points. Now, this is obviously a very low permeability well. This is a well that I picked up from a colleague when I was short course teaching in Mexico. It had about 45 years worth of data at that time. It was in a very tight, very low permeability region that had been developed in the 1960s. It was in a remote area in northern Mexico, so there wasn't a lot of service for the well. They essentially just let it produce its entire life. There were a number of these that they gave me, and they all had exactly the same appearance. So very, very tight gas well on the order of 1 microdarcy. Okay. This is a shale gas well. I'm almost 100% sure that this is a Barnett well, but it may not be. It may be a Haynesville well. But regardless, you can see very nice performance data, very flat, very hyperbolic looking over here. And then we run it down, and we're going ahead and fit it again with all 3 models. And we notice that not really bad. Model 1 seems to be pretty good through here, and then Model 2 and 3 have some extrapolation back into here, which maybe is a part of the tuning. But then when we look at the cumulative production, the performance profile is almost identical. So perhaps we should just say, hey, this looks like it's a pretty good match. Little bit of difference between Model 3 and Model 2 and 3. So probably needs a little bit more tuning, but suffice it to say that all 3 models gave very consistent results for this particular case. Again, it's a shale. And then we created some functions. My student was in love with this so-called beta derivative. Every graduate student has to fall in love with their problem. And his was a ratio of derivatives. That's what the beta derivative is. And what he does is he shows this for a tight gas case. And so this is the area where we actually had the behavior well known. Over here is a little bit of early time behavior. And then out here we have no information. So you can see the behavior is sort of like a rainbow over here and then a rainbow over here, because we simply don't know what the right answer is. But fitting or regression wise, they all fit this intermediate data range. Okay. So with that completes the presentation. Looks like I'm just about right on time. It's 37 minutes after. Let me entertain a few questions, and then I apologize, I have to go to some exams. So I want to thank you for the opportunity to present and meet with you. If there's something I can help you with at some other time, please let me know. And again, I appreciate the opportunity to speak, and thank you for the invitation. So I'll stop now and take any questions for the next few minutes. And I'll have to repeat your question so that I'll catch it on the recording, just so you know I'm only recording me. Okay? Thank you. Sure, that's a great idea, actually. I am not seeing, it must be in the chat part over. Oh, wow. Okay, so the question is, are there any models that differentiate between matrix and fracture system production. Wow, somebody's done their homework. There are actually several models that consider that. There's a trilinear flow model produced by Ozcan and his students. There's another version of that presented by Matar and one of his colleagues. These, to me, are very difficult to tune, that is to match, because we don't actually know the properties of the system. But it's a great question because what you really want to do is you want to try to match each part of that production profile. My advice would probably be, rather than to try to uh, match that part of the profile, would be maybe to look at doing an RTA on it, perhaps doing a full reservoir simulation as well. So any of those could be a possibility. Do we have another question? Okay, so I'm probably going to have to repeat this, and you'll have to correct me because I think I lost my train of thought. I was thinking about the answer rather than the question, but you're essentially saying, can we correlate completion size and type with production performance, or the analysis of the production performance? Is that what you're okay? So answering that question is like grabbing um, a snake. There is no way I'm not going to get bit. So anything that I say, someone is going to disagree with. The people who do the fracture modeling are going to have their opinions. The people who do the fracture diagnostics are going to have their opinions. The people who do reservoir modeling are going to have their opinions. The people who do geomechanics are going to have their opinions. But what I can tell you, and I thought actually, I need to write up this work, but I did a lot of case history analysis, and it was proprietary. I couldn't share it. It was, it was consulting, if you want to call it that. And what I showed was you would look for a characteristic signature, and then you would compare the other wells against that characteristic signature. So there's 39 people on this call. I'm pretty sure all of us have, two eyes, two ears, a nose, a head, hopefully two arms and two legs. We all look different other than that, but the genetic signature or the physical signature, I should say, is correlatable. And for a long time, I had been creating these correlations by simple comparative analyses, and then using the completion size and the completion parameters, as well as a few reservoir parameters, and trying to correlate and predict behavior with those, um, uh, I'd say, master model, if you want to call it that. Now, the way that would work is you would have to somehow have a robust data set. You'd have to know how much water you pumped, how much sand you pumped, how many fracture stages you have, how many clusters per stage, maybe even how many perforations. You'd have to know something about the reservoir. You probably wouldn't want to compare parts of the reservoir that are not geologically consistent. But once you start with that, then you go back and you have that information, and you can compare these production profiles, and then you can take those comparisons. There'll be comparison parameter on the vertical and the horizontal. So there'll be a scaling of both time and performance. And then you can compare those time and performance cases. I'm going to bring up the chat. Let's see. That's going to come over here. And then what we would do with that is we could use, I know this is a big word for your generation. People call it machine learning. They call it augmented learning. They call it artificial intelligence. But what you're essentially trying to do is find a correlation between parameters and physical behavior. And you could do that. I actually saw a presentation last week where a company had used a machine learning approach, taken all of the completion information and all of the production information, put it into a database, about 30 parameters, and then took several hundred wells and put those into the database and then showed how well they could match each well. There were some great matches and there were some terrible matches because there's always genetic differences. And that's why I would prefer to look at the individual rather than the entirety of the group and make a comparison. So me personally, I would compare well by well. That's not to say that someone will not sell you, or you maybe even on the presentation line here, that you wouldn't want to create your own tool to do that. I would just ask that you go back and check by hand. I'm not as old as I act, and I'm young at heart, but I do think you need to look at your data physically. You need to observe behavior, and you need to make sure that the behavior is consistent. We did have a project again about 10 years ago with one of the people that was co-author on most of this material, and he was a truly phenomenal computer programmer. He pulled data in from all points on the earth, and he was able to help me make some statistical inferences about shale plays. But we had terrible outliers. You know, if you have a case where you have 15,000 wells, 2,000 of them may be unanalyzable, and you have to accept that, not spend that time on that. Okay. Sorry, I'm very much approaching my time to go to the other exams. So I probably have time for one more question, if that's okay. Sure, sure, sure. You know, this is a good question because I did a lot of abnormally pressured gas analyses back about 20 years ago. If you send me an email, I'll direct you to the work. But it was the usual abnormal pressure gas work where people were looking at P over Z plots. And, you know, for those of you on the call who are not familiar, South Texas, Northern Mexico, Gulf of Mexico, there's a tremendous number of abnormal pressure cases because these formations were deposited very quickly, and the overburden is actually supported by the reservoir fluids of gas, if you want to think of it that way. Um, I'd have to look at it, but once you're below the normal pressure line, the hydrostatic line, I would assume this should work fairly well. Again, if I'd want to look at the actual data cases, but once your production is below the hydrostatic, I think probably these methodologies will work. They may work before that, but you're going to have to account for that nonlinear behavior due to the overpressure. So where I'm going with this is at some point you're going to have pressure dependent properties. And I, I mean, the software, certainly the vendors have this in the software. They have a permeability modulus and a porosity modulus that you can use. But then it becomes a history matching exercise. I just want to be really careful that I don't tell you, yes, you can do this, but then, you know, the details are in how you tune that uh, that particular model to the data. So love to have a case to comparative, to look at comparatively. So if that's okay, I hate to do this, guys, but I'm going to go to my other meeting. I did save this video, and sorry if I did forgot to mention the question. The question, which the is not being recorded, was can you apply these methods to abnormally pressured reservoirs? Sorry if I wasn't more clear on that. So thank you very much for the questions. Thank you very much for the interaction, and I will post this video for you. And I will assume that your coordinator will send the link to everyone once I send it to her. Okay. So my apologies. I'm going to stop sharing and jump over to my next meeting if that's okay with everyone. Sure. Thank you, everyone.